So at this point, the farsighted people in the audience might be like, hey, what about me? I have problems with my eyes too. And I'm like, cool, yeah, I get it. You have problems with your eyes, and I'm going to tell you how to fix your eyes too, okay? All right, so the physics of farsightedness. A farsighted or hyperopic person, I'm having trouble reading this. I think it's my myopia. I have to move this computer a little bit closer to my far point. Okay. There, much better. A farsighted or hyperopic person can usually see distant objects clearly, but they cannot focus on objects nearby. Whereas the near point of a young normal eye is located about 25 centimeters from the eye. Okay, that's the near point is the closest point that you're able to read, let's say a book or something, without it getting blurry. So the near point of a farsighted person may be considerably farther away. So it could be several hundred centimeters away. So you can't read this book here, but you could read it if it were over here. All right. So the lens is designed so that the eye perceives the light to be coming from a virtual image located at the near point of the bad eye. Okay. So if you have an object right here that you're reading, okay, your corrective lens must make it appear as though the image is really coming from over here, which is the near point of the bad eye. Okay, so let's see what this looks like in practice. A farsighted person has a near point at 210 centimeters from the eyes. So that's the closest they can read is 210 centimeters. That's 2 meters away. Poor person, right? And so if I have an object here at 25 centimeters, which is supposed to be my near point, okay, I want to make sure that it really seems as though this image, according to the corrective lenses, this image is coming from 210 centimeters away, okay? How would you, first of all, what focal length would do that, right? And how would you use the thin lens equation to come up with that focal length? Well, we do what we've always done. We write the thin lens equation. We want 1 over the object distance plus 1 over the image distance must equal 1 over the focal length. Okay? Now remember, we want to take an object that's at the near point, in other words, 25 centimeters, right? And we want to put it at the spot where the person can actually see. We're just helping the person. We're giving the person what its bad-formed eye needs, okay? And this person's bad-formed eye needs to be at 210. Is that correct? Yeah, 210 centimeters. So what focal length will do that? Well, if I go ahead and solve for f in this situation, I get a focal length of 28.4 centimeters. And notice that is positive. What does a positive focal length mean again? A positive focal length simply means that this is a converging lens. Okay? So if you are correcting, by the way, one thing I forgot, the image is going to be virtual again because it's forming on the same side. So again, here's our corrective lens. Here's my eyeball, right? I have an object that's at 25 centimeters. 25 centimeters. And I want my image to be formed over here at 210. This image is on the same side of the lens as the object, so that has to be negative. So I knew you all caught that. But when we're talking about corrective lenses, the image distance is always going to be negative because you're forming a virtual image on the same side of the lens as the object is. Okay? In both cases, whether it's nearsighted or farsighted. All right. Now, a positive focal length means a converging lens. Great. We know that. Is there anything else I want to add to that? Not really. In the next video, we're going to talk about the refractive power of a lens, which is measured in diopters. This is, again, something that's very useful for optometrists and ophthalmologists because this is the units in which our corrective lenses are actually given. So like that little number when you get your prescription for your eyeglasses or your contacts, that is given from what focal length you need to correct that vision. Okay, we'll discuss that then.